All right, we're live. Bob Null, thank you for acknowledging my test. Okay, give me a second to get situated. Okay, so we're live for Synacor Challenge Part 6 now. Um, and where do we leave? So, time travel. Yeah, basically the theme of last chapter was time travel. We were working with an emulator layer over our VM. So we have a VM model that just executes the bytecode, an emulator layer for interacting with that. And part of the reason we have that layer is that we can add commands like this, the ability to undo a command, the ability to save a command history so that we can replay that. So if you'll notice here, when I started up Synacor, it started me right at the ruins where I have the teleporter in my inventory. So I'm ready to use the teleporter and run experiments. Um, and the experiment I wanted to run was to set the value of the 8th register and see what happens when you teleport. So right now, apparently nothing happens. What's actually happened is that what's happening under the scenes is that the Synacor universe is doing a check on the value in 8th register. Um, and it's seeing that it's not a good value, it's setting it to 0, and then you get the default behavior. So if we're able to figure out what bytecode is running when that check is being performed, then we can take that bytecode, disassemble it, and figure out what value we're actually supposed to get, thus enabling us to bypass this altogether. Actually, I'm still not sure. Do we bypass the check or right, even if we have the right number, the check is so expensive that we might still want to bypass it. Is that right? So we have to get the right number and we have to perform the check faster. I mean, I imagine we could do either. We have plenty of freedom here, right? Once we're allowed to control the registers controlling the universe, then we have all the power. Um, but we'll start by exploring that bytecode and seeing what to do with it. So, wish list. Um, we are, you know what? I'll call this done. We can rewind state and we can even replay it. A lot of this could use a little bit of polish on the UI side, but I'm not going to worry about that until it becomes an issue. Um, Same here. This is an ongoing thing. We're emulating at a higher level already, but we want to do other things. So the first bit is running the bytecode and PC locations. Yeah, log the running bytecode. I remember this assemble said bytecode. Do we have any sub goals for this? I think we'll just start with something very simple. Maybe as a debug command for our VM state, we'll provide a method that allows simply printing the current command that's about to run, but translated. So translated from machine code into assembly. So this is the first part of this assembler, straight to text, and in fact, actually straight to the standard output. Then we can see later if there's too much standard output to deal with and figure out how to deal with that then. So phase one, print currently running bytecode or instruction. So we can jump right into our VM state and we've got our step function here. Okay, so a typical command. So before we tick our VM, you got to the same point tonight. You spent a few hours in starting at assembly, but haven't gotten past it. Oh, cool. Yeah, I'm glad someone else is doing this. That makes it more fun. Um, I'm guessing that at my pace, you'll probably get to the end before me. So I trust you not to do spoilers and whatnot. But yeah, we're gonna take our time here a little. Um, phase one. In fact, let me see. What other phases might there be? There's gonna be print. Um, maybe we have model the assembly language. This will be useful for disassembly, but also assembling our own instructions. Useful for an ASM DSL or parsing instead of going straight to string. And that'll be nice in case I imagine it won't be necessary, but I could imagine also extending this challenge beyond once it's done and writing my own compiler so I can inject a whole line of code, right? So I could take a DSL in Scala describing some computation I want to perform and then have that translate into assembly, which is then injected into a running machine. That'd be very cool. Um, but that is long-term goals. In fact, we'll put that at the bottom of our wish list with a question mark. ASM DSL, a compiler even, but certainly a disassembler of some sort, like maybe even a disassembler. So right now our plan is just to show the running assembly. Um, I would like something that shows disassemble to like a high level language. So stretch goals or bonus parts after we have finished Synacor. Okay, so back to our VM state. Um, all right, so our VM ticks from instruction to instruction. Within each tick, there are multiple steps that run, right? And the VM progresses through various states. You can only tick when you're ready, and the tick that you emit um, always contains a ready VM state. In fact, we could even say, if we were to rename this to state, rename to state, and assert that it is ready. Let's see if that works. If that still compiles. We could even say that a tick by default, so it always has a val state. And all of these are extending a tick type, right? Okay, so we only tick from a ready state to another ready state. But how does this work? We take our instruction pointer and use that to find an opcode, and then potentially 3 different arguments. And now we just want to insert a step that prints the current command. Zuno, you made it. Good to see you. So yeah, we are just starting here. I'll put up my I should put up my checklist to the right, or rather my wish list. Okay, so we're gonna be very simple for our first step. I'm just gonna print translated machine code as it's being run, and then eventually we'll do something more fancy and maybe like get a list of like parsed assembly that actually has some semantics that we can play with. Great, so we only need these. I think let's do a show, def show the upcoming command. And I think we can also assume that we are in a ready state when we're doing this. Otherwise, the instruction pointer might be pointing somewhere that doesn't make sense, right? So ready, maybe not even updated. So we can only show from a ready state. And this will give us a string to print. And this show, well, we'll take our enum. So we'll take our op. And in fact, I don't know what an enum looks like to string. I think it should just be the name that we set it. But like we could verify that in our play worksheet. If we have, okay, so we can just test our show function as we're moving along here. On my right shoulder, we have a start VM already, and we'll test the show function as we iterate over that. So we'll print the opcode, and then we'll print all the arguments. But now, let's start with that, depending on how many arguments there are. So it looks like I'm doing this thing again where I match on the number of arguments. So here's next instruction. Similar kind of thing. I've written myself into this corner because I didn't want to be able to arbitrarily do math on an address. So address only has these three methods where you can increment one at a time. But we're still matching on the number of params because we don't want to print an argument that isn't actually an argument for this function, right? So case 1 or case 0, then we just print the operation itself. And it'd probably be helpful to have the address. So let's do PC, our program counter, as a hex. And we'll do a colon. So at that address, we're running this command. And then we have each of 1, 2, 3. I've got to learn the macro for filling 1, 2, 3 vertically. And now we have, we can just show the words for now. But we'll need to have some way to interpret that. Oh, we don't need B here. I suppose we do want hex for all of those. Dot hex. Dot hex. And I've missed the curly braces, so forgive the typing here. Okay. So right now that's just going to print the words, but we can at least test it. So in our initial state, the very first command issued dot show. Well, we have to make sure that compiles first. Oh, you suck at programming. Hello. I enjoyed your live streams with Bad Cop. And yeah, I hope you do this in Synacor too. It's been really fun to do, and I'm excited to watch other people do it too. I think another AOC streamer, who was it? Um, oh, Liquid Cake is also gonna give it a shot. So, um, there's spoilers. But you might already know that you end up messing with a VM. and probably already guessed that you need to do some reverse engineering. So we are just at the very start of reverse engineering, printing bytecode. So this is probably where the true spoilers start in about 20 minutes or so. Oh, right. My show command, did this run? It did not run because I suppose this has not compiled properly yet. Give it a chance to reload that. And yeah, that's fair enough. It's really fun. Did you by chance do the int code puzzles from 2019 Advent code? Because it's similar in spirit to that. We are still not showing that as a member. Um, let's see, probably we're not compiling yet. So yeah, we actually do have issues. That's why it hasn't compiled. Enum case does not extend. Oh yeah, I added that. So I need to make sure all of those extend. Extends tick with its own state parameter. There we go. Oh, and let me get rid of this to do. Alrighty, well, if you like one, you'll like the other. For sure. By the way, I started seeing your shorts come up on my YouTube before the AOC season. So when I saw you doing AOC, I was like, oh my god, it's you second programming. I very much enjoyed your shorts. They've been nice, useful bits. And I still haven't finished your Bash course, but I want to go through that. Oh, what did I do here? I seem to have erased some colons accidentally. All right, let's get back to a compiling state. Um, oh, what is it supposed to be? Extends tick with that state. State is a tick. Extends tick state. There we go. Cool. Enum case does not extend its enum class tick. It is extending tick, so output is extending tick. As far as I can read, yes? Great, great to hear. Well, thanks for stopping by. I hope you have a good one. Um, am I missing a paren here? Output has those parameters. It extends tick with its own state. Yeah. Alrighty. Well, you know what? That was a digression we don't necessarily need yet. So let's comment that out, and we can handle that later, because I don't want that to get in the way of what we're actually doing. So we have an enum. We don't need to extend the enum class there. Okay, that should get us back to a compiling state. Or close. So we found a thing we required a tick. This dot continue with ready. Oh, continue. Where's the tick? Oh, that's where it is. I accidentally wrote tick here. So state is a VM state. A tick is the end result of running a tick in our VM, and it always contains the VM state that it came from. So I think that was the issue earlier. I botched my multi-line edit. Okay. Things should be working again. State equals this. This was actually last previously, so now we'll just rename it to state. Um, unsafe set ready. Shouldn't affect anything. Anytime I type unsafe, that is scary. That's something to check. Okay, now we can look at our show function. Now we can look at our show function. Not quite yet. We still have this should be a ready state. So that's interesting because this is referring to, we've already proved that this is ready. So I'll just add the unsafe set ready there, but I'll have to debug that later. Okay. Now we can show what the very first command is. Oh wait, yep. And the very first thing we do is a no op. Interesting. Cool. Now we can do this. So we can do start vm.tick, and then get its state, and then we do a show. Let's see what the second command was. State is now a member of tick. Oh, right. That was that refactor I was doing above earlier. So let's revisit that refactor because I want to be able to do that on any tick. So we have our enum tick. We can remove this commented code because I know we botched a multi-line. And so all of these will extend tick by passing along its state as a parameter there. Tick now needs a parameter state, which is a VM state that is ready. Okay, and in the case of halt, it was the most recent VM state before it halted. So if we called state dot show, it should always show like a halt command happening. Same with in, except it would show an input command happening. Is it same true for output actually? Let's see how output is used. I just want to understand that because understanding this helps me understand, I don't know, the cleaner my model is in my head, then the cleaner I can make the model in the code, and vice versa. So case out. Yeah, so that's after progression. That's after progression, after we've done everything. So there is some slight inconsistency here, which I don't like, and I'll make a note of that because we can make something cleaner. Output and continue dot state both refer to state after the transition. Meanwhile, input and halt don't have a state that was after. All right. So it's somewhat of a lie to do this, and maybe that's not what we want. But at least in this case, it's probably going to be a continue. Um, that state that show that hasn't compiled yet because value state cannot be accessed as a member of Synacor at the tick from MS. Oh, state cannot be accessed because I didn't put val here. That makes it public when you say val. And I suppose these need an override modifier. I do still think this is somewhat of a mistake. So maybe what we want would show is optional. We only show if this is a running state. Is for an input to get the next state, first we have to pass in a character. So we could always pass in a dummy character to get that state. But still. And in this case, what shows well, what shows on a particular VM instance is the current command that's about to run. What tick.state is might be the state before we're about to run the command, or the state after, which I don't like. It should always be the state after. But we will live with that for now. And, as always, if you are seeing a cleaner model or you understand something I don't yet, you're allowed to speak up. Oh, Hyper Game Dev, welcome. Thank you for the raid, the YouTube redirect. I don't get notifications for that, so I appreciate you giving me the heads up. Let's see, last time you were here, was I working on Synacor? Because we have progressed a bit since then. Bad Code Guy, welcome, welcome. So let me give you a quick welcome here. How was your stream, by the way? I hope it went well. Okay, so this is part 6. We've gone through 5 days, but each of these days have been fairly self-contained. So I think it shouldn't be too bad to drop in at this point. For the Synacor challenge, we started with a binary, right? So we were given a binary. And we were given a spec, an architecture spec for a VM. So we started modeling that VM until we got to a state where we were able to run the binary. And then we created like an emulator layer on top of that so that we can interact with a running program. And then the running program in question happened to be this little text adventure. So you might be seeing that on the bottom left here. This is a classic like Zork style text adventure. And so we get to run around in that text adventure, solve the puzzles in there, and eventually we learn about teleportation, which, according to the laws of interdimensional physics within the in game universe, teleportation is controlled by the registers that control the universe. So those registers are the registers of our VM. So in order to progress in the adventure game, we need to be able to do some ROM hacking from in game and modify the state of the running VM as like a with like God mode powers to be able to progress. So we got a running VM emulator. Um, we started giving ourselves some God mode powers like time travel. Uh, so we can record our history, replay commands, basically have save states. We've added save states to our emulator. Um, and then we've added the ability to set and change registers. But now the register has some magic that happens when it is set. So we need to inspect the actually running bytecode. So right now, you can see on my bottom right here, I have added the ability um, to show the currently about to run command, and it's been decompiled a little bit so you can see um, the address at which the command is running, as well as the name of the opcode that is running. So that's the start of disassembling the machine code, and then we'll inspect what comes out and try to figure out what kind of a program is running. Might not show well on. Oh, fair. Yes, the Synacor. I need to get commands that work on both YouTube and Twitter. Not Twitter. Twitch. Um, but it should also be in the description of my YouTube video, so I think you can click around there if you'd like to see the stream notes. Yeah, so I work with the VM machines. Yeah, I don't. It's not very often I've worked with a VM, and they've usually been toy things, or like I've implemented a VM. But for this one, yeah, we had to model. It's a very small spec, so we had to model a virtual machine. Okay, so we see our first couple commands. That's good. Now we kind of need to figure out what is our interface at the emulator layer. Well, actually, let's look at this from, yeah, emulator layer. Great, great. Hmm. So I could give my emulator, say, modes. I could turn on, because this will do a lot of stuff. Um, or like running when we run the game, every see, even printing this is a lot of commands, so we can't just have that run constantly all the time. I think I want to be able to turn it on and off. And yeah, turn it on and off as a super command and just like print between. I think I might also want to give us ourselves at the console layer the ability to tick once at a time and then inspect the code at that tick. Oh, and just to demonstrate my super commands here. So there are the normal commands. You know, we could look at an object, we could help to get like the help menu. This is how you interact with the game world normally. And I've added some things like input log. So this is all of the commands I've printed, I've used up to this point to get here. And I can do undo, which lets me backtrack, right? Hmm. Okay, so um so we have this command progress until blocked. And I suppose this is a time when we really want to show ticks, show commands, because I don't really think we want to show what's happening during an input. So that kind of solves our problem earlier with certain ticks not actually having a current state, like an end state accessible. Because the tick is sort of incomplete, right? Like and the tick that comes from an in command is incomplete until a character is input. So you don't actually have that tick yet. So I think this might be the place where we do this. State.tick. Yeah, we take that state. Let's just do this for now and see what it looks like in the terminal. So I'm going to take our state.show and we're going to print line that from our continue commands. And I suppose we might as well also do that for the out. But that will get very noisy because that will interrupt our, you know what, let's not do that because this here results in like printing a character. Well, actually, it doesn't result in printing a character. This results in building a string. So it wouldn't interrupt each character by character. Let's just do that. Recompile, log into Synacor. Now, when we boot up Synacor here, we don't start at the beginning of the text adventure anymore because we're skipping ahead to a save state. And it's taken a second to compile. So while that's happening, we can look to our VM state because I suppose the next thing we'll want to do is improve our show command a little bit. So def show. Okay. So when we show, we're just showing the hex command of all the argument parameters. Some of those are actually going to be registers. So I think I want to print this. So let's say we have a command like add. That's the opcode. So we have some address at 0x, you know, 0888, right? We run add. And we might have 2 parameters, 3 parameters. What's the third one? The third one in this case would be, well, A is a register at which to add. So this is going to be something like R, R1. In register R1, we're saving a value. And those values might be literals. So in this case, let's say we're adding 2 plus 2. We would have that. But now we also have a case where we're adding the values of 2 other registers, right? So this could be R2 and R3. But in this case in particular, I think I would want to show the values inside those registers. So maybe register 2 and register 3 both have this value 2. So we're adding 2 plus 2. I think that is what I want to print. And maybe the fact that this is a destination register, this R1. I'm seeing a pattern here. um, what we want to do, so suppose in this register 1, we want to say something like we're storing into register 1 the value of R1. So this is actually at a lower level than the actual bytecode or the actual assembly. Right, we could say store, I'm making up assembly here. It can be like into R1 goes this value, add R2 plus R3. And the reason I bring this up is because this kind of mirrors the code we're writing here in in our evaluation loop. So this evaluation loop, what it's doing is progressing the state. Each step, store or progress, gives us a new VM state. But it could be more general than that. What this is doing is building an AST, and that AST could describe two things. It could either describe a state transition, or it can describe an expression. So this could be a big digression, but if we wanted to do it, what we could do is have these commands build up an AST, and then over here we have a way of printing an AST, and that's how we print our assembly, or our decoding. And then we could have another interpreter for that same AST, and that builds up an operation that transitions state. So that's we'll add that to our wish list for later because that's a thing I like doing. It can be very clean, and then we can do like some kind of I don't know. We can make like a free monad over our assembly DSL. So state so VM state transition AST. We absolutely don't need that, but it would be cool. It's the kind of thing I like to do with DSLs, and that would make this a worthy DSL. Because right now it's you could call this a DSL sort of, but really it's just a bunch of method calls. Yeah, I'm glad you like that idea. Anyway, we're not going to do it that way. I think we'll stick with this approach here. So in the case of a register, we'll just show the register name. And the fact that it doesn't have a value should be enough to say that that's what we're storing to. Um, but now that means we kind of have to do this case by case because whether or not, like, whether this second argument is interpreted as a register or not depends on completely depends on the command, right? Not completely, like it won't be as verbose as this because a lot of these cases are very similar. So we can lump together cases. So I'm gonna take a shot at that and see what that looks like. We'll call it show two for just the time being so that doesn't clash. And we're gonna match on the operator itself. So operator match, exhaustive. And now some of these are very similar. Um, so mult, mod, and or, these are all binary operations, right? So we can do this. Whoops. And lump those together. And just to make sure these things compile for now, I'm going to throw in some triple question marks. Okay. So add mult, mod, and I'll do that. Or does the same thing. Greater than or equal to, do those work that way? I'll think about that again in a bit. Well, actually, let's take a look. So greater than, if one is greater than then, so we compute a boolean from that, and then we store into A. So it is the same kind of pattern where A is a register that we're storing to, and B and C are potential values. So let's add greater than and equal to there. GT EQ. Um, Great. And do we have any other binary options? I don't think we do, but if someone notices, let me know in chat. And then what other operations are similar here? So JT and JF obviously have an address that you jump to. So we jump to b.address in both those cases. And we look at the value of a register. So JT and JF, let's lump those together. So value of the potential B register, right? Get stored to A. All right, and so we're not doing a bunch of back and forth here. Let's just go ahead and implement this so we have an idea of what all of these will eventually look like. So we have our program counter address. So let's do it this way. pc.hex. So at that address, we have A as a register. So we need the register name for A. We need a toString for a register. So let's look at that real quick diversion. Or you know what? We can do that later. So A, we'll give that a proper toString. Store into the A the value of that command on B and C. So how we interpret B and C depends on whether B is a register or not. So we'll call it B expression. So B dot reg. So if it fits U15, so if B fits U15, then it is literal. So we can just do B dot hex, right? Otherwise, it is a register. So we would print the register name. So here we have B. No, yeah, I guess just B. And then we have the parentheses, and then we want the value in that register. So this is a dref, I believe. Dref. And I remember my dref wasn't an actual dref. Let's look at what it does. If the word fits U15, then we get the value. Otherwise, we get the value from the register. So this is a part where we're actually dereferencing it. But it works either way. But I do want to rename that because it's actually register.dref over here. That's like an optionally dref. And that is a literal value in this case. So dref b.lit. And we do the same thing for the A expression. So a.hex, otherwise we get the name of the A register, and then we dref a.lit. So our expression becomes A, B expression, and C expression rather, C expression. You recall loading Z80 assembler via CN90 cassette tape. Ooh, that's cool. Retro. I never did that. I got to talk to a lot of people that did that. Oh, this is an if. By the way, I donate to the Computer Science Museum in Seattle. It's a very cool place. I gotta see a lot of old machines. Um, what's wrong here? We're just setting values. Okay, yeah, that's fine. Okay, so we can print that. Um, let's look at our zero operation commands. So there's no op. Um, there is halt. Let's put them all here. So there's halt. There's no op. Set push pop. Pop has no arguments, right? Oh, you know what? We have a place for this in our code somewhere. Um, hey, right here. Oh, right. Everything else is no op. uh, right. That means our zero parameter case can just be this. So if there are no parameters, we just type. I guess it's similar to the start of this. And the name of the command, no B or C. Sky Opium, welcome. What are we trying to do? Well, the broad picture is that we're doing the Synacor challenge. If you want more details, I'll give that to you there at that link. But right now, in the current picture, we are examining bytecode from a running program, right? So this program is running on a VM architecture that's foreign to us. We've implemented a VM that can interpret that and run this program, but now we need to be able to hack that program. So right now we're adding a way to view the currently running operation. Right, you can see an example here in this worksheet. So we have our VM state, and when I do this command show, it shows us the current address and the the machine instruction that's being run. So the very first instruction that's run by our address is a no op. It just does nothing and progresses the counter, the instruction counter. So we are able to print those. Let's go back to our list of opcodes here. Right. So we are looking for all of these that have only one parameter because they might have enough in common. So push and pop. What do those do? Def pop, or let's see, case pop over here. So its parameter we store in a.register. So we need to interpret a as a register. Um, and that's fine. Oh, hold up here. I'm just realizing here. So in our way of printing binary operations, here is the register to which we are saving, right? So my expression there is going to be a little bit more complicated. It's going to be a dot reg. So we verify that that thing is a register. And then our register itself will have a toString that gives just the index of the register itself. Rather than the hex code for it. And this thing here could probably be extracted into a helper. You've never seen anything like this. Ooh, well, it's fun stuff. Yeah. Um, Reverse engineering is not your day-to-day programming task. Okay, so in the case of pop or push, so we're pushing the value of A. Um, I'm gonna give myself a helper function for now. I'll call it def show. So this is for some word that might be a register or uh, we'll call it reg or lit. And this gives us a string. So this is show, we'll say, no, we'll say show arg. Yeah, let's call it that for now. And we can formalize this more later. But like I'd like to be able to type reg, like the type reg or lit, because that's what that is. And right now we're just saying that this word is supposed to be a register or literal. And let's take this if expression here. Okay, so we'll make this parameter. Yeah, it is a reg or lit. So if reg or lit fits U15, then it is a lit. So we'll say b.lit.hex. And then we have an else case here. Otherwise, we take the B register's name. So b.reg, and then I suppose we could just make that a .name function. For clarity, if nothing else. So we'll add a name method there. And then so we get the name of the register, and then we show parentheses, and then we dereference our reg or lit to a lit, and then we just print that thing's hex value. And then we close the parens. Okay, and that is this example here. Right? And this one here would just be like just the value itself, a literal value. Okay. These things that like the variable name here, that should actually just be the type. This comment shouldn't need to be printed. So this is telling me that my DSL isn't quite expressive enough yet. Let me catch up with chat for a sec. You're too much of a beginner to understand anything, and the screen is very much like a blob for you. That's fair. That's fair. I try to make this accessible as we're going. So if you have at least some background, um, it should be the case that everyone can keep up with the smaller problem, if not the bigger problem. But the smaller problem right now is just printing this. That's to recompile these after. Yeah, so we're given a ROM that is already compiled, right? And what we do is we just right now we're just like rerunning the ROM, and we're not injecting anything into it quite yet. But every time we load up, we rerun the ROM. And what I have right now is a save state basically created by replaying all of my commands up to a certain point. So I replay all those commands, and when I boot up, I go to a save state to a point of interest where we have in our inventory a teleporter. Alrighty. Oh, back in your day, you hacked US businesses using an electric drill. Fancy. Hacked them through the power outlet, huh? There's some truth to that. Has anyone ever used Ethernet um, over power outlet? So I did that for a while. You can run your home internet through the power outlets and have like plug in two access points at the power outlets. Yeah, power over Ethernet. I had to do that because I had too much latency on my home Wi-Fi router to play a game that I wanted to play that required low latency. So I bought that, and it didn't have the same bandwidth, but it had enough latency, or low enough, consistent enough latency that I wasn't getting ping spikes while playing my game. What did I just do? Just deleted something. Um, okay, so I think I want to implement that register.name because now we're using that verb and we gotta be able to compile it. So do we have extension methods for a register? Yeah, so a register, we can do def name. And I suppose we could match on these values. So R match, and I'm just going to copy paste all of these. And in those cases, we just do a string R whatever value. Oops. How do we do this? Multi-line coding. All right. There's got to be a nice way to do that. Um, but hard coding it is perfectly fine by me. It gets it out of the way. Okay, back here, that is compiling. That is compiling. And now we can do our string for this case where there's only one argument. And with pop, we are storing to a value. So let's do this bit here again. And what are we looking for? Wait, we are storing to a register. So this is just a register name. We take A, interpret that as register, a.reg.name. Or we actually still need the op. So yeah, the op. Okay. That's fine by me, but not all of those are actually storing. So pop stores, push stores to a register name, right? Let's see. No, it pushes the value of A. So we've got our reg or lit function. So push is in a different case. Case push goes up here. Pop stay down there. Jump is jumping to an address. So that doesn't go here either. Call is calling from an address, right? Or it's jumping, it's also jumping to an address. So jump or call both have one argument, which is an address. Out and in are special. Those will probably never happen. So in this case, we only have pop. Okay. So out and in, we are just going to keep those at nothing for now. Let me catch up a little. Oh, you still use your extend kit as a doorstop. Lovely. Um, a power line adapter instead of power over Ethernet. I guess, yeah, you're not doing power over Ethernet. You're doing internet over, right. Yeah, power over Ethernet would make me think that you're powering something via an Ethernet cable. So basically, USB-C cable that can do everything. Yeah, power line adapter, exactly. Um, let's see. Push. We need oh, what happened to our reg or lit function? Did I accidentally delete that earlier? Or no, yeah, that's the show arg. So in one case, it's actually a reg or an address. Right. It's either a literal address or a literal register. So we're reaching kind of the boundaries of our current model here. We'll call it show address. And if it fits U15, we do b.address.hex, and we're gonna color it a little bit. We're gonna put an @ sign so that we know it's an address. I think we also want to know the value in there, so we'll want to deref it. Oh no. It would be a literal address. I don't think we want to show what's in the address. Yeah, I think that's fair. And then again, we do our reglit dot address dot hex. Okay. Not the cleanest modeling there, so I don't forgive. Well, I forgive you if that's a little bit harder to follow than it needs to be. But we could at least use that function in this code to make it more legible. So in this case, like our B expression would just be show arg for B, and show arg for C, right? So my main goal at this moment is that it's legible here at this layer. And we can worry about the implementation details later. So in the push case here, we have an address. So at yada yada, pc.hex, same thing we always do. We're doing that often enough that maybe we want to just have a helper function for that. And the operator, And the argument, we're pushing to an address. So case push. We push a.value. Oh, no. We're pushing onto a stack, sorry. So you want the value inside there. So that's a literal, potentially a literal. So reg or lit from A. Yeah. You got AI to dump CRT green Commodore pet ROM font using Python. Fun. Yeah, this console color scheme I'm using, I just had ChatGPT generate that. It's all green right now, but oh wait. Oh, hey, this is from earlier. Let's see what actually happened here. So this is everything that runs before ruins happens. I think this is what happens in the look command. Yeah, we've got some machine code. Okay. So let's do something like I don't know. Let's just look at our inventory. This is the code that runs when you look in your inventory. And yeah, right now it is just a bunch of hex words, right? And I'm trying to make that a little bit more legible. Have I ever messed up with Home Assistant? What's Home Assistant? Oh, like uh, set ChatGPT to like a Home Assistant that can run things in your home? It only made 1984 mistakes. Fair enough. Yeah, smart home stuff makes sense. No, I haven't. I haven't done that. I think I'd worry, but I don't have a lot of smart home stuff. The smartest stuff I have is like all my Elgato lights, I guess, Wi-Fi connected lights. That's about. And there's a Roomba in here, but I don't love having it. I would love having all my home stuff up connected if it was just like ad hoc hardware that I was installing and it only ran on like my network and didn't connect to the internet and like I had actual control over it. But a lot of these things don't even give you that much granular control, right? Like you have to use their app, um, and you can't actually do anything fun with it. But I think I would enjoy tinkering. It's a classic joke. The S stands for security. 7FFF should be the max, yeah. So these 800, that's reference to register 1. So this is not a literal value, but a register reference. So that's saying we're going to save into register 1 the value of, oh, these are also registers. The value of register, save into register 0, this is the value of register, whether or not register 3 is greater than register 4. Okay. Um, and I already liked our VM state model. But what I'm liking about doing this right now is as we are trying to print everything, we're kind of hitting the edges of a model. Um, and finding new places to make it more coherent. Self-made smart home only. Yeah, totally. Okay, so reg or lit A, right? Because when we're pushing we're pushing the potential value of that. Okay, and when we pop, we're storing in a.reg, so we don't care about the value in there, so we're just getting the reg name. Here, reg value. Now set. Set stores in A the value of B. Set has two parameters. So let's just copy this over. So we're storing in A's name, the value. So this is our little value expression. The value of B. Okay. Now in the push case, we've actually already handled both push and pop. Jump or call also take only one argument. So what are we doing when we jump? We take the address, which might be in a register. It might be a literal address. It might be a register. So in this case, we have the operator. We have our function show address. And to that, we'll pass A. So store into A the value of B. Where was that here? Set. And the value of B is done this way. Okay. And we combine that with call. Does call work similarly? Case call. So we push the next instruction, so it looks a little bit like the push, and then jump to an address. The address is the only parameter there. Oh, hold on. Jump actually takes two arguments? Is that what we were seeing? No, jump only has one argument. Oh, no, that was set. Okay, set has two arguments. Jump just has an address. Wait. Hold up. I think I messed up here. So store into A the value of set here. Store into A. A is register name, the value of B. Okay, and in jump case, A is an address that we're showing. And it could come from a register. Cool. And in the call case, call A is an address. So we're calling an address, we're calling a function, then jumping the address. So call is just like jump, except we first save our current address on the call stack before we commit that jump. So it makes sense that these two have a very similar definition for print line. Jump true, jump false. Value of B stored to A. Okay, in both of those cases. No, I don't think it's actually that. Jump true. We get the value of A, and then we jump to B. So we jump to the value of B. So we're going to have basically this, show the value of B, and we store in, we do that by looking first at reg or lit in A. Okay. Right. Potentially. Um, and I hope as we're doing this, you're kind of seeing that this is actually kind of similar to this code here, in that here we're calling all these little methods here to kind of do a runtime type check on these. We're saying that this is a register. We're saying when you say b.value, we're saying that this is either a literal or a register that's referencing with a value that we interpret as literal, right? And address similarly is either a register or a literal address. So we're doing all of this here, and we're kind of doing that again here, but instead of calling that dot reg and dot show, or like dot reg or dot value or dot address, we are calling these methods that print those names. And it's that similar structure that makes me want to have the AST idea, build an AST, and just build multiple different interpreters for that AST, one of which makes strings, and one of which builds state transitions. Because they do share the same structure, even though their behaviors are very different. But making it explicit here will just help us kind of figure out what exactly that structure is. And then I don't know, maybe if we had an AST, we could do other fancy things with it besides these two, right? That enables more fanciness in the future. Okay. Not has only one argument here. So we just take show arg, I suppose, but for the value in A. But does it store something? Wait, not. No, not takes two things. Right, it stores into A, and it uses the argument B. Alrighty. So we just do the same kind of thing, a.reg.name. You don't have a reg or lit function? Oh, no. That was show arg. Show arg. Right. Show arg. And then show address. Show address, show arg. Cool. Oh, very cool. AST is a domain of Antler and Tree Sitter. Totally. Okay. Call, I imagine, might be pretty similar to. Um, oh, wait, yeah, we already did call. So that's done. How about return? How does return work? So return, we pop. Oh, we just pop. There's only one argument, right? Let's look at our one argument functions, numparams. Okay, push pop jump call out in, and then return is one of our zero argument functions. So we can just delete that line because it'll be caught here. I actually do want to make this explicit though. That way, when we compile this, it will tell us what cases are missing. So no op, return halt. All of those have just all those have no arguments. So we just show the operator. We're gonna ignore out for now, and then we have read mem and write mem. So let's look at how those case read. Okay, no, case rmem. Okay, in the case of rmem, A is a register. So let's get our framework here again. Um, hmm. We're missing op in a bunch of these actually. This is why we shouldn't copy paste, and we should just have functions that do this. Um, hmm, I'm thinking about how to extract this, and I was thinking for a sec about making a function that does this much and then has multiple, like a variable argument for strings for every argument, right? And we could just pass those along in here. And all of these could just be like, we pass along the number of strings that are necessary. And then we do like a make string at the end. I think that's a worthwhile diversion, or not even a diversion. So let's see. I mean, it could be the same method name. We always start with this, which is well defined. So let's start there, and then we have args, which is string repeated, and this whole thing returns a string. So we show our address and the current operator name, and then we take all of our args and we make a string. So args that make string with a space between each. Okay, I think that's fair. And then now something like this would become, let's say show args multiple. That's what we'll call it. Show args would become just this bit here. Show arg a. Yeah, then we can start making those one-liners. Um, I would want to do this with like a regex find and replace, but I don't have that in VS Code. This is why you do stuff like that early. So we'll do a very quick manual refactor here, and as we're doing that, we can double check that what we're writing makes sense. So the arguments here is that, right? So in set show args, we have a register ID and then just a normal argument. And when it's jump or call, there's only one argument, which is an address. So show args, show address. And same kind of thing. And in all of these cases here, we have very similar code. Oh, let's show args. A is a register. It's a register to which we're storing things. B is a literal or a register reference to a literal. And C is the same. Oh, this should actually be show arg. Jump if true, jump if false, depending on whatever the value of this is. Right. That makes sense. Not show args. This only has two parameters, the register to which we are saving, and then the register or literal that we're performing not on. Read memory, we have a register name to which we are saving what we read from memory. Oh, read mem. And then B is actually an address. So this isn't show arg, this is show address B. Okay, this gives us a chance to review our code as we're doing that. And then write mem. A is an address. So show args. Show address A. And that is the memory address that we were writing to. And then show arg B, because that is a value. Now out, can we actually do out here? So case out, we just progress and we output whatever is in A. And, right, we're just outputting that as a word. I think in this case here, we were dereferencing that word. Right, because it might be a register. Yeah, I can't imagine that we're ever turning so output turns it into a character. So I can't imagine we're doing that with an address. So I'm going to go ahead and say that this here is actually a reg or lit, right? So we're going to say show args and then show arg A, because that's either a register or a literal value. Okay, so that is fully implemented. I think we can delete our previous show method here. This is the one that was generating all of that, and we can replace it with this nicer one. Okay, and show arg isn't actually just show arg because it doesn't work on any arg, it works on literals. So we'll rename that symbol to, I don't know, show val. It doesn't let me do that right now. But this reg or lit here, this is actually reg or address. So we'll rename that there. Okay, .address.hex, .address.hex, those both have an at in front of it. Address should also have a like print line function. And we need to change the order of that in the string so it compiles. Reg or lit. It's actually reg or dress. Okay, are we compiling? Show is not a member of VM state. Well, it ought to be because we just oh, we need to rename it to I think we named it show2 for a second. Here we go. And we've got just one error left. And what is it not like here? It is not an exhaustive match. Great. Let's look at that in the REPL because that'll give us a better. Oh, I just want to see the full error message. Rocco was crash saying Scala's object functional meta language tribe on shoulders of Lisp on JVM. Is that because Grok can't handle saying the truth? And so, hi. You may ask, but whether I answer depends on how weird your question is. Oh, great. This is good, and it's good that our assertion failed because we found some place to improve our understanding. But look, we're doing stuff. Jump to address. Oh, wait, jump to address 6? Does that make sense? Yeah, okay, jump to address 6. I thought for a second that I was maybe seeing a register. But no, we've checked that. So we have a bunch of require assertions. I think we need better error messages with those require assertions. So we're going to go back through in the next bit and fix that up. So if you're going to manage a code base for the rest of your life, should you use Scala or Golang? Scala can use JVM libraries like Java, Kotlin. Yeah. So the ecosystem is vast and mature. Well, before I answer that main part of your question, so Scala can use JVM libraries. That, for the most part, doesn't matter a lot. There are a lot of libraries that build on popular libraries used by Java devs. There are also a lot of libraries that are pure Scala all the way down, so it's already a mature ecosystem just on its own. And usually, as a Scala dev, you want to avoid the Java library or like the library that's written for with a Java API. Usually, if a library like that is popular enough, someone else has written like a Scala wrapper for it. So that's what interop is like with Scala. For the most part, you're never really doing much interop, and the source code that you're using is usually Scala source code. You have to like jump to source many times before you see like Java source code. But yes, it is a vast mature ecosystem. And if you're managing the code base for the rest of your life, Scala gives you the tools to, I think it gives you more tools than Go does to make that code base manageable. Where they differ is managing culture, right? So part of the, if I understand correctly, part of the motivation for Go is like, hey, let's really simplify things, dump things down. So that there's like kind of one way to do things, and it's very verbose, right? So like verbose code like that, that is not really polymorphic or ad hoc, can be difficult to add functionality to or to like change the functionality of, but it's at least predictable in that you know what people are going to write when they write something. So Go solves this cultural problem at the level of the language, right? The language prevents the culture from diverging too much. Now, Scala has a lot of freedom. Um, and it's happened on teams where, there might be one or two people who go hardcore down the FP rabbit hole and they don't take anyone else with them, right? So they've learned all these concepts and started using it, and their code is beautiful and perfect, good for them to work with there. But then they've left the rest of their team behind. So if you're managing a code base in Scala, you have to manage it as a team and make sure everyone's on board with what you're doing because Scala is very flexible. You can use it in many different ways, and you can do FP Scala and you can do FP Scala in different ways. So for the most part, there's like a standard way to do FP Scala, and like the community has converged in the last decade. And like that's part of what came out of Scala 3. Things that had become cultural norms were baked more into the language. Um, but yeah, you have to solve the culture side on the side of your team and make sure that people are on the same page if you're managing a code base in Scala. But otherwise, the language itself gives you plenty of tools for a long-lived code base and making that very manageable. You're motivated by Godot. That's a good motivation. What was that? Let Q be what was that? Console.log. Oh, are you asking what this error is? Let's figure that out. I mean, we can see real quick from the stack trace, we tried to call .reg. Um, and yeah, when we called from int, we had a requirement fail at line 63 in that package. So let's go to that line, and that's the first of our require statements that we will yeah, we're gonna go back, look at all of our require assertions, and give them proper error messages. Starting with this one that's giving us trouble, which is register.fromInt. So package numbers register from int. Okay, if we're interpreting something as a register from int, it needs to be between those values. Let's see, invalid register index, we'll just say that. Invalid register index, and we can show what the actual in was. And let's call .hex on that, or 2-hex string. Oh, right. Yes, the YouTube crowd is coming from a Godot stream. Makes sense. Wait, you were doing Godot, right? I don't know if I missed some of your chats earlier. My younger brother is wanting to learn Godot, and I've told him he should learn it on stream. You get plenty of help that way, and like motivation to stay on track. Okay, so there's that. Let's look at our other require messages in here. Yeah, let's drop down just one screen here. Require. So when you convert a word from int, we check that that fits in there. Cool. Other require messages. There's not a valid unsigned 15-bit integer. Oh, we've already added some of these, haven't we? So it's really just that last one that we needed to add. Okay, well, where are we calling this register from int? Or rather, where are we calling it that's causing an issue? So in Word, when we call .reg, in VM state in show arg 128. So def show arg. Oh, nope, in VM state. Okay, we call .reg in here somewhere. Oh, what's going on with B? We're not supposed to reference B. We're just showing this word in particular. So show arg reg or lit. So reg or lit.reg.name. Okay. Otherwise, we dereference that. Oh, yeah. Well, there's some evidence. I'll let him know. I've also told him he could learn Scala, and then I could help him a lot with that. I think Scala would actually be a decent. I think it has a decent learning experience for new programmers altogether. Okay, well, look at this. Um, we weren't getting this earlier. Now, these big out loops are a little bit annoying. So we're always showing what's in register. So the game starts with a couple of no ops, and then it just starts printing something at that. Out is a out's parameter is a register though, right? So def out. Yeah, and when we have a show def show for out, we show arg, which might be a lit. Hmm. So what I'm seeing here is a literal. We are printing all of these literals. Oh, let's interpret that as ASCII. So let me pull up another Scala console here. While that's loading, I'll catch up a chat here. You think it's good to learn more general languages? GGScript means everything is stuck on that engine, but teaches you Python pretty much. That's fair. Yeah, a general purpose language. um, Learning Python, learning Scala. I think I think having a static type system that at least stays out of your way, like in Scala, um, would be helpful too. So, like to my brother, I'd probably recommend him Scala over Python, and partially because I can help him along with that. Because you can treat it like Python. But yeah, in general, that's a good idea. And Ogham the Bold, he won the physics prize and did maths a year early. 1984. Thatcher put me in forced labor camps. Godot is a constant. Okay, I get it. I get it. Godot. So 0x0013. That two character. What character is that? Oh, that's taking a second to load. Yeah, so that's a space. So it starts by printing off a bunch of spaces, and then it jumps to an address. And at that address, we do more no ops, and then we jump. This is weird. This is weird. And then we jump to an address. Then we jump if true, jump if false. So this is sort of just like testing these functions, I guess, before actually doing anything. Jump if true, the value at these registers, we would jump to 445. So if any of these are set to anything other than 0, so it checks what the registers are initialized to, right? And if any of these are set to anything other than 0, we jump to this 445, which I assume fails us. Or maybe not. Maybe not. Maybe it does something cool. And maybe we should. I'm now curious what happens if we start the game with values set in those registers. Because no other operation sets values in those registers, right? And there are these jumps. Jump true, jump true. So that should jump because this value should be interpreted as true, right? But it doesn't, apparently doesn't jump because it just moves on to 1e47 or 1e7. Interesting. Um, so even though our thing is not working, this is already interesting to start to read. Yeah, they are starting to look familiar. Oh, and of course you've seen this before. Okay, so I'm interested in these and what's going on there. So let's just look at the spec. We'll pull up the spec on the right while we're reading that. Um, okay, so we have things like jump in here somewhere. Jump true. If A is non-zero, jump to B. Okay, so A is non-zero, so we should jump to B, which is 432, the address 432. Um, but we didn't jump there. We just went on to the next instruction. But we know this works because we're able to run our VM emulation, right? And we've been doing things for a while. Oh, also, this isn't the very start of the game. This is only printing. No, this is the very start of the game. Starting emulation, and we're printing everything from the top. Okay, I'm gonna gloss over this jump true bit for now because that's perplexing me. If someone can decode what's going on there, let me know. I'd be curious to hear your interpretation. But this next bit is checking that all the registers are set to 0, and we'll jump to this code if they are not. I'm curious what happens at this address. So I want to test that. Let's add, well, we'll keep that in our head for now. We want to test that. Don't let me forget. And then we set register 1 to that value, then jump false. So jump if this value is false to this. So this seems to be like where we go if we're failing various tests. So that shouldn't, this is dead code unless you unless you hack it. And we set to R1 and then we jump true. So this is another error case. So it's already doing a self-test, which is interesting because when we first ran the program, it printed a welcome message and then it said it was performing a self-test. But it looks to me here like we are already performing a self-test before even doing any. Well, I guess this whole output, I guess this output might be the welcome message. It's just perplexing me because they're all the same address. Yeah. So maybe I wrote a bug there. Maybe I wrote a bug there. Because all of those would be spaces. Oh, the instruction at 01F4. Let me see. That one you're looking at. Oh yes. Yep. R0. Yeah. So my register names are 0 are 1 indexed. Is that fair? Should they be 0 indexed? So R1 is 0x or 8 0x8000. Um, we can have, if you have strong opinions, we can have a debate in the comments. Hmm. Okay, so a lot of self-test stuff, and then this happened. 8000 is not a valid unsigned 15-bit integer. So that probably happens in our print again. So inside of show arg, we're calling .lit 127. Let's take a look at that. Show arg 127, we're calling .lit somewhere. Dereference a register and do .lit. That should be illegal. If it fits U15, oh, it's this line right here. If reg, oh, b dot, b is not our parameter here, it's reg or lit. And we've got the same issue here, reg or lit. Okay, well, let's run again. Yeah, all the leading outs should have different values. Yeah, let's debug that real quick. What's going on in our out? So we show args, arg a, oh, yeah, we actually just fixed that bug, I think. Yep, because this formerly said B. So those two things are the same bug. This is just a soft failure, and then this one here is a hard failure. Okay, so now we should see that. But now I think in our out command, I don't think we want to do show. I don't think we want to show arg. I think we just want to show the character that's being printed. We don't need to show the literal. So let's take A. Let's deref that so that we get a word. And let's do .lit.to character. And what's the issue here? Oh, no. I think that's just on word. We turn a word to a character. Or, no, I think we do as character because we're not actually doing like conversion checking. I forget. As character. Yeah, on a word. We convert a word to a character. So first we dereference, and then we do that as a character. But actually, I want to have show character different because if it came from register, I want to show what register it came from. So we'll do reg or lit. And we know, I guess we know it's lit, but what we're going to do here is just do dot as character, and that makes a string. I don't know, two strings, sure. And in this case here, we want it wrapped into parens with the name of the register dot as character dot to string. Okay, so we have a show character, and now in our out case we can do show character. Show is Scala superset Lua? You know what? Scala does use one indexing sometimes. So in a tuple, so at 345, dot underscore one is going to be the first element of the tuple. Underscore two is the second or whatever. But in a list array, any kind of collection, then that's going to be zero indexed. But this isn't really an index, right? So _1 isn't an index value. It's more like a name. So in this case, the register is a name, which is kind of why I think of it, I don't know, as R1 rather than its index of 0. So it's 0 index at heart in its implementation. It is stored in a vector that's 0 indexed. But the name, oh, what was our error here? Top chat is censored. See live chat. Oh, am I missing something? Oh, Hyper Game Dev, good night. Sorry I missed you if you're out already. But yeah, thanks for the redirect. Oh, yes, I get what you mean. So in YouTube chat, you can look at either top chat or live chat. Hmm. I think I'm getting live chat. Now, what's the issue here? Reg or lit, did I mean? Yeah, I probably meant something else. Let's look at that. In our show character method that we just created, um, reg or address. Yes, I meant reg or address. Okay. Good night. Okay. Invalid register index 6. Yeah, it should be 8006. So this is happening in show address. Let's look at show address. Deref a register. Oh, b.reg name, reg or address. Jeez, this is hairy. I want my type system. Mm, because deref should always take register as an argument and return a U15. That's what it should actually do. If we had this in the type system, what would be happening is like we take a word, we try and interpret it as a reg, so we have an optional reg, and once we have a reg, we then deref that reg, and then the U15 is what we can convert to an address. But we haven't fixed that yet. -1 based indexing, yes. Um, okay, I think that is fixed. Was there another thing I wanted to fix just now? Let's try that. Oh, yay. There's a lot of assembly. And this is going to be assembly for the entire program because we are replaying all of our state. This should stop at the first input. I'm expecting it to crash. Also, interesting. I have a pretty big lag on my stream actually. Um, oh, what happened here? Oh, it's printing a new line. Funny. And non-zero exit code returned from runner. Wait, where's my error? Did it like crash without an error? This is so weird. Okay, I'm gonna run last here to get what the thing was. Last run main. That's it. I have never seen this happen. Non-zero executor. Um, yeah, I've never seen this happen from while running a Scala program. So it's from the runner. It's not from my program. Did I flood the terminal with too much output? Is that what happened? But anyway, we're able to print something that is pretty reasonable. I'm going to disable the replay for right now so that we just do um, the initial bit and power on self-test. So I want to see the code for the power on self-test. And hopefully that shouldn't crash anything. I was expecting when we hit the in command for this to crash. I'm actually surprised this even compiles because it would fail in the pattern in, and in should show up at some point. But I suppose we're only showing continues. We're only showing continues and outs. So that becomes a non-issue. Okay. Well, let's go to our main method. And let's not load up the shortcut. So here's the shortcut. We're feeding the shortcut, and then we do the look. I think if we just comment all of that out, then we're no longer doing the shortcut. So we get to see the bytecode for just the initial welcome message and power on self-test. And there is so much of it. And now this isn't the bytecode of the compiled binary. Okay, and then we finally get the in. So this is everything until there. Yeah, this isn't the bytecode of the compiled binary. This is, oh, that's a value that we're printing. This is just the instruction that happens to be running at the moment, right? So it's not like we're disassembling yet, but it'll probably have, similar code. Now, does this history go back far enough? I don't know where the top of that was. Yeah, my terminal history doesn't actually have enough for all of that. Yeah, so this is a point at which we do two things. Let's go back to our to-do list. Now let's go to our README. We can print the currently running instruction. I think we want to do more. We want to log the running bytecode between two PC locations. So this involves turning on/off the printing, right? So we want that, and we also want to be able to save it elsewhere. So, I mean, still standard out, write to file. Yeah, I think maybe you want to write that to a file. And interestingly, so this crashed when we hit the in case, right? Because we don't have a show for in. Now what's actually happening, if we go to our emulator, Every time you run a continue or an output and progress the pointer, we show at that point the state. And the state at that point might be like our current instruction is in. So we're still going to see the in commands. So now that gets me thinking about the in. What happens when you do an in? We wait for a character. Then we progress to a new tick. And it's a tick that happens by running that in. Right? But that's going to be a continue tick. So I promise this is going somewhere. So an in goes to a continue. This dot input, right? So we store the value to a register and we progress, and then we ready up. So this is a tick. This is an input tick that tells us what the next thing is going to be. And we consume that in the emulator. So here in the feed, we have that input and we loop around to a new tick. So when this thing ticks again, this tick could be a continue. And when that continue tick prints, it's going to print the next command that's about to be run. So I think every command does get printed, would get printed. I mean, for now, we are only doing the print line here. But if we look at every continue, so I'm trying to think about if an in happens between two continues, and it's like a kind of meta tick, right? If you continue, yeah, in your continue, you have your current state, and that state, or you have your current counter, and it's pointing at something like some instruction code. That instruction could be in. It could be add, right? It could be add. If it's add, it does add, and then it gives you the next tick, which has the next instruction. So the next tick is a continue. We have two continues in a row, right? But what if you had add followed by in? Then in the first continue tick, you would see that in instruction. And then you'd run that in instruction right here and get that next tick, which progresses. So the first continue tick shows the in instruction, and then the second tick, which is an input tick, has a state. It doesn't have a state. We have not yet made this next state. So that input tick is a virtual like tick, I suppose, because this thing here turns into a tick, right? An input. No, it turns into a state. So that's how you make the next state. And then that state gets used. So here's that function that makes the next state to get the actual next tick. And after the input finishes being used, this next VM state could be a continue, right? That has another in. Okay, so here's what we just discovered here. While thinking about that, if you have two, Yeah, you have two VM states, right? There's two VM states. If you have, I have my ticks, right? I've just realized that my ticks don't correspond one to one with VM state, right? You could have two continue ticks with an input ticks in between them, because our input tick is really just this. It doesn't correspond to state. It has a character, a function that takes a character to a new VM state, and that new VM state is used to create the next continue tick. So even though there were only two ticks or two states in either case, whether it's continue or continue input continue, yeah, in either case there are two states, but in one of them we have three ticks. So we lied a little bit about tick, and that's why we couldn't do this. Right, a tick doesn't have a state. Well, because the input doesn't have a state. Like a tick is not an actual complete running of an instruction. It's just the output of our like step function for progressing the state. And the output of this step function is like, oh, I can't finish progressing the state. Please help me by providing me a character so I can run this function to get my next state. All right. All right. So it's only the continues that need to be printed. Um, but that means if we go back to our emulator, that means if we go back to our no, not our emulator. If we go back to our printing, our show methods, we should have a reasonable definition, a reasonable way to print this show in. So case in, what happens in, we take an argument, which is let's see, def input. A is a register to which we are storing. So we do show args a.reg.name, and then we do show our and I guess we have a C. C. What do we do with B? Okay, you gotta look at the spec there. Okay, so we have in here just above my shoulder. I think it was number 19. Okay, read a character from the terminal and write its ASCII code to A. It can be assumed that once input starts, it will continue until a new line is encountered. This means you can say, okay, right. Read character from the terminal and write its ASCII code to A. Oh, C is a character. It is not a register. Right, I shadowed C. I'm gonna rename this to CH. Right, that's not an argument. Okay, so we store it's just register index. Um, it's like pop. So pop or in both collapse that same case. Uh, hold on. Read a character from the terminal and write its ASCII code to register A. Cool. I think some of these might be able to be collapsed to the same case. Show args. Right, not in RMEM. Actually follow the same pattern, don't they? That's kind of surprising. Okay. Well, now we should be able to run this again. It won't crash. Had a little digression there where I realized what my ticks really are. Tick means debt in English. The first 5,000 years. Oh yeah, I read that book. Or I didn't read it. I listened to it as an audiobook. It's quite the tome. Um, it was interesting. Look. Okay, so this is the first welcome message, right? The foothills, everything, all that. And this is the bytecode associated with that. So this is what is running live. The instructions are running live, not the actual bytecode, because there might be like procedures that are being called, right? So we call the thing in R6 this procedure, and we jump to that address. Yada yada. It's interesting that we don't have like all of the outs. Oh, here. Oh, what's going on here? A bunch of pops out, exit, exit. I don't remember this happening. No, no, no. There are two exits, right? That's this part here. There was an S there too, right? ASCII? Yes. The spec does say ASCII, and Unicode needs at least 2 bytes, right? Like it's 2 bytes for the most part, but then special codes allow you to like do multiple or something like that. But this is only U15. All the literal values are only U15. Okay. So this is the first kind of helpful thing we can read. Um, Another helpful thing would be just actually taking the code and disassembling it. So the code in memory, disassembling that rather than just showing the running instruction. Um, and the most helpful thing would be if we actually had a proper disassembler that tried to decompile the code, or a decompiler rather, into something that made some sort of a sense and like gave us names for all the functions that are being called. Mm, let's step right along with our README. Let's at least be able to configure this behavior. We are not seeing, okay, we see the very first in call here. It might be nice to see what's happening between the ends. So we only show states. Let's look at our emulator. Oh, nope, no, no. Emulator. So we've only been showing instructions during our progress until block loop, and we've only been doing that for like a continue and output. Um, but we could also do that during our feed bit. So during continue here, I suppose we could also take the output case. That shouldn't happen, so we don't need to worry about that. It should be dead code. But we can also print line here, state.show, so that we can see what's happening as we are consuming input. So I'm gonna let that run. Then we could see I don't know, the response to, well, you can see if there's something happening between individual input ticks. And then we need to, I suppose, have like a show enabled or we could start appending to a log. Let's look at our main. This will give us a visual on how we run this. So we can halt, we can undo, we can oops, we can get the input log. So case, we want to be able to like enable and disable printing bytecode. So there is a show instructions. Right, something like that. We could do like a start log of instructions. And then show what we logged afterwards. So enable op log. Yeah, that's what we'll call it, the opcode log or the operation log. So enable op log. We can disable the op log, and then we could show the op log. Show the op log. Cool. That seems pretty reasonable. And then maybe a way to clear it. Clear op log. All right. Let's implement those methods. So we have our emulator. There's now an op log, and right now it is just list of strings. Actually, let me see. I think we might want to know the current address. You know, it very well could be the case that every time we're at this input prompt, we are at the same address. So that might not be too useful. But I'd kind of like to know all the addresses that were hit. But we can just parse that out of the op log. So we have an op log, and that's going to be a list, I suppose. I don't know. Let's make that another queue. Key of strings are appending to, and op log enabled. Is no, is a boolean. I can feel VS Code lagging, and I have no clue why. So let's first use this op log enabled. It would end up here. Oh, I guess we have a log function. So def I guess we could log a tick that is a continue or an output. So log tick, we'll make this a private def. It's just a helper. And that gives us an emulator. Oh, hold up. I suppose we're building that up as we're in this loop here because we don't have intermediate emulator states. So that's not quite what we want. So we start with disable and enable, I suppose. So if oplog enabled, then we print line show. And then we run the loop. And then we have ops, I suppose. So this is a queue of string. So what's actually going on here is that we loop passing along ops.queue state.show. Otherwise, we do what we were doing formerly. We loop ignoring that. And I'm going to make this a default parameter with just an empty queue. Queue.empty. That way we can just not run that code. Like the if else could be in here in the third branch. But I like having it in two separate lines here. Case continue state. Right. And that's the only one we care about in here. But now we're doing something similar here, but we're doing it twice. This thing returns a tick at the end. I suppose now it's returning a tick plus a potential list of ops. So where's the end of our loop? The end of our loop happens here, tick. So let's return tick and ops. The ops that got us there. So val, the next tick and the ops equals loop. And we call that loop with ops starting out empty. Okay. And state equals next. Oplog enabled, or like we have an oplog queue. I think we could can we just override the oplog queue? Or should we append to it? We should append. Oplog equals oplog dot queue all. And we just iterate over ops. Okay, so that's back to compiling, I think. As return type here, the return type should be tick followed by queue of string. Queue is not a member of ops.enqueue. There we go. Okay, and then we do the same thing in here, except we're kind of doing it twice. So there's a string, there's a tick. Um, out next. You know, I'm gonna change the order of these so that it's kind of a. I'm gonna change the order of these down here. We're gonna put the tick first, the tick, and then the string, and then the up log. So Q of string. Okay. So we have the same if else in this loop here. Um, I don't like that this is proving tricky to generalize. So ops Q string, or at least I'm not seeing it right away. If anyone can see how to generalize this. So the tick continue. We take our ticks, we take our cars, we take our ops. Okay, so that code follows. Now output does exactly the same thing. So both of these cases have a state in them. I suppose we could do file state equals, and then we match on the tick. Right, something like that. I wish I could just do, if we ordered those together, so let's say we had def foo with a tick that was either continue or uh, output, right? In a union type, should I not be able to call, I don't use union types very often because I usually have a proper ADT, but t dot state, oh, they both have state, so we can call t dot state. Cool. Okay, yeah, we can generalize this. So case t, which is of type t dot continue or tick dot output. Oh. And since both of those have state, then we can do t dot state dot tick, t dot state dot show, t dot state dot tick. Yeah, and we can remove this output case. Okay, great. That does generalize. Oh, output. We got a sporadic character there. And what's going on here? Oh, the return type. So the return type is the string. Let's put the tick first. So the tick is first, followed by the string, and then followed by the Q, the ops. Okay. We assert that next is blocked. Cool. And yeah, I guess blocked means not able to run an instruction currently. Or not able to run it to conclusion and get a VM state. So The continue in tick is basically a function from character to an actual tick. Um, and we do the same kind of thing here. Does that work? Okay. Now we can turn it off and on. Oh wait, we still need to. I think we'll call it toggle op log. So def toggle op log. I'm hating capitalizing log there. I'm gonna say op log is actually just lowercase log. Oh, no. Crap. So any iteration of op log, case insensitive, we're just gonna turn it into op log. Yep. So everything except toggle op log. So toggle op log should have a capital there. There we go. So this gives us a new emulator state, which is basically this copied with oplog enabled flipped equals not oplog enabled. Okay. And with that, we can go back to our REPL here. So enable and disable, we're going to just change that to toggle. And when this happens, we're going to pipeline and say oplog enabled, and then just look at the value of that. So emu.oplog enabled. Okay, but before we type that, we should actually change the value. So emu equals emu.toggle oplog. There we go. So we can turn it on and off. It's going to start off, show oplog. So in this case, we can just print line each of these. So emu.oplog for each print line. And then clear oplog. Let's go back to our emulator and implement that real quick. Def clear oplog equals copy with oplog set to q.empty. Okay. So emu equals emu.clear oplog. Okay. Great. Now we can look at the operations where we mess around with the teleporter. We can get that bytecode, and that might be a good little cliffhanger. Leave it for ourselves. And of course, more importantly, like we don't necessarily need to interact with this from the actual game loop, right? Now that we have this, we can go to our worksheet and just play around with actual values and explore there. So we don't actually need these commands. As long as we have an emulator that lets us do these kind of things, then we can do whatever you want programmatically with that emulator, rather than just sending commands that interact with the emulator. I think it's cool to have it there as like a God mode shell. Yeah, let's try that out. Oh, also, let's skip ahead. So let's uncomment that. That lets us skip to where we have the teleporter in our directory. We also do still want to be able to diff memory. So let me just add that to our list because I kind of lost track of it. Diff log running bytecode, yeah. So we can turn on and off line printing. Write to file, I guess it's still a question mark. We might want to do that. Um, this is half done. Print currently running instruction. I'll say it's completely done. Ability to inspect state. Diff to states. Yes, I think we do want this. You want to diff memory in particular. So the reason that this goal exists is because diff memory when picking up teleporter. That's one thing we might want to do. Like diff memory when moving rooms, right? So we want to know like where those values are saved in memory, and then if it is like a consistent spot or anything, we want to know where those variables are. Let's go back to our emulator because I think there should still be some compile errors here, specifically init. We need another empty queue, q.empty, and then we have false, so oplog starts disabled. Okay. How's my stream health, by the way? Because it seems like my computer is struggling a little bit. Is it time to kill JVM? Smooth sailing over there? Okay. Good to know. I do have my OBS process explicitly prioritized over everything else. So even if like VS Code and everything else is lagging, it should at least try to get make sure that's going. But I feel it. I definitely feel my computer stuttering. And I can see it in my task manager. And I'm sure HTOP would show us something similar. My task manager is saying that my VM, my WSL VM, is taking most of the CPU. Well, that and OBS. Starting emulation, and then nothing happens. Wait. Oh, because we're running through everything. We are jumping ahead to our state. It's moving. It seems like it's happening slow, which surprises me because when the oplog is disabled, nothing should be happening, right? In these loops here. If oplog enabled, then we do that. Otherwise, we do nothing. I mean, we are appending an empty queue to an empty queue, but that shouldn't do anything. You just started reading the Synacor doc. Ooh, great. Are you going to take it on yourself? Hmm. What is the holdup? Okay, let's just test. I'm just going to delete some code or comment out the code that deals with the oplog altogether. And in fact, you know, let me just kill all Java. Kill all -9 Java, because that's usually the source of my stuttering. Okay, if oplog enabled, then yada yada. We just comment that out. Now we're back to our old code, right? That's basically all I introduced. Okay, everything is good as new. And now when we run this, yes, yes, sword coffee for sure. That's gonna be a thing. That's gonna be a ritual here. Oh no, my computer. You know what? Maybe it's not actually Java. Maybe it's just that my computer can't handle streaming with 3 screens. I haven't even started Java and I'm already stuttering. Fair enough. Um, you don't actually even need to implement all the opcodes to get it to start running. Eric was in here and he kept prodding me. He's like, "Hey, you know, you can just run it." And I think he wanted to see me just run the game because it explicitly says that you only need to implement in, out, and whatever else. I think I actually missed content. I think I missed content by not implementing the other things because remember those addresses that jumps to if it fails? Like maybe there was a message there. Yeah, yeah, okay. So I'll do that. I'll make sure Eric knows that I did go and do that. Um, and I'll also tell him. Yeah, I didn't have to debug it for very long, did I? But yeah, I'll have to tell him that I found it. Without needing spoilers, that all we had to do is look at the bytecode and be like, hey, what's this address it's jumping to? So I'll have to break my VM for content to find that to find those messages. Okay. Yeah, that's why he was prodding me so much. Um, right? He wasn't just like trying to like help me make incremental progress. He wanted me to not miss that content. Okay, I'll wait until Eric Wastl is in chat, and then I'll let him know I thought about that, and that we're gonna go see what happens if you try to run with a shoddy VM. Okay. Um, this is too slow. My computer can't run. Um, do I just kill all WSL? Let me just htop WSL. My stream's gonna die at this rate, so I can feel it. I can feel it happening. Uh, yep, I need to do a WSL shutdown. Let's just do it right now. The initial test is very forgiving and encouraging. uh, yeah, basically I didn't even try to run it until I'd implemented them all except for the in opcode. And then the last remaining, at that point, there's only one bug, I think, and it was that um, I wasn't dereferencing registers that pointed to addresses. I was just assuming that they were literal addresses, right? Oh, and there were like a couple spots where I forgot to progress. But we found that before I think even running into that error, right? Because of the tick type system. Is it dying because you're running a VM inside of a VM instead of a VM? Maybe. Yeah, I'm running Synacor inside the JVM inside of the hypervisor for WSL. Uh, too many layers deep. But no, I think. Oof, could be my thermals. There's one way to know if I'm thermal throttling, and that is by checking my performance and looking at the clock speed. So I'm not getting thermal throttling, like we have the proper clock speed. I think it's just a very busy CPU, right? Um, VS Code, we can close. Um, Dismiss that and close because we already have the thing we need there. So we can restart WSL. We can take a look at that bytecode, and then if we can see that bytecode, I think that can be our chapter close. And next episode is making sense of the actual bytes. So I want to see the bytes that run when we are trying to run the teleporter. Okay, so cd get out that code. Um, Run main. We'll just go straight to the run main. I don't have global variables though. I don't have many of them. Okay, let's look at what processes are running. Well, I'm glad the stream health is okay and that we're at least getting that across. I'm feeling my laptop here and seeing how hard it is, or how hot it is. Suspiciously, one vent isn't very hot, right? Like usually when it's running hard, um, all the vents will be hot. Oh, wait. No, no. It intakes from the bottom and pushes out to the sides, which makes me suspect like thermal throttling, but the clock is running at a normal speed. So I don't know. Maybe this is actually a hardware issue. It's not, and I'm just blaming the JVM because I like to hate Oracle. Oh boy, I don't think that's gonna run. I mean, if I were to stash this, would it then run? Because like, what's the diff here? Gdiff source main Scala Synacor emulator. So what did we do? We added a couple parameters, oplog and oplog enabled, right? Um, and then we added ways to mess with that oplog. And of course, this starts out disabled. So if it were enabled, then we would continually like enqueue the show of the current instruction, right? That's what we would be doing. But we have that commented out. So we should be just doing what we were doing previously. And what we were doing previously was working, just running the game. So I find it surprising that this is a struggle. Let's just start by loading SBT separately. Right. Even the WSL is tough to load. So it might just be that given the stream is too much work for my computer, for my laptop. And I don't know. We might have to continue later. It has like an enforced bedtime. You've been working me too hard. We need to go you need to go sleep. It'd be a little bit unsatisfying to end right here though. So we'll give it another little shot. We did decent work today though. So we can at least start summarizing. Um, so we did some semblance of like show for instructions, right? So we can show registers as these names. Um, I think this whole thing could probably be cleaned up a little bit. Like maybe I should actually just use show all the way for everything and make a show instance, use a type class for this. I think that'd be pretty reasonable. And then like we had a way of showing arguments, right? And this is revealing a little bit of the boundaries of our current model. So we need to clean that up a little bit. But a register or maybe a register that holds a literal value, or maybe a register that holds an address. We did all that to enable showing these instructions here. These are grouped up because a lot of them have the same kind of pattern. In particular, all these binary ops have the same pattern. There are cases here where grouping them up didn't really do much. Like not and read mem are not really conceptually similar. They just both happen to have one register as an argument. Uh, Same here. Oh, no, two registers as an argument. This has one register as an argument, right? Um, and then that enabled like all of our changes to the emulator. Where's our emulator code? Yeah, so we added an op log to which all those show lines were recorded, and we can toggle that log on or off as we are running through from like I guess command to command. Um, and to use all of that, where do we have it? We have it in our main class. We added these commands here. So input log, toggle log, and show log. And now I want to combine this with the commands we got last time, right? So we have our replay of history. So we want to jump to the place when we have a teleporter. Then we want to change the value in the 8th register. And um, I think I think we need to be able to write the oplog to a file because I want a diff. I want to go um, use the teleporter, see the code that happens, and then I want to change the value in the 8th register, use the teleporter, see the code that happens, and then those two things, I want to diff them and see what happens differently between those two runs. And that I think is where we'll see So I don't think we're on a proper cliffhanger until we're about to do that. um, but if fate is saying that we must end, then we must end. Let's see. Let's try to run that. It seems like my computer's had a chance to rest there while I was talking. Starting emulation. TV Josh, hello. You implemented a few of the opcodes and got a message from the default input file. Oh, cool. Yeah, I'll get there. I'm definitely curious. I want to go see now, but don't spoil me yet. I don't know if there are other input files. There certainly weren't as part of the challenge. I think they would be like fan made. But part 20 out of 8, way down the line, we could actually just write a Synacor compiler. I don't think I'd want to make it like an external language. I think I would just want it to make it like a DSL within Scala. Um, and then a way of compiling that DSL down into Synacor bytecode that we can then like save and run and whatnot. Um, what's actually happening? So I think something is actually happening now. Um, that is my fault. We're at a point where I can stop blaming my computer because I think my computer is running all right. Yeah. Yeah. So we've done something. But did we finish the summary here? I think we basically did. Okay. Let's finish this last bit then. Let's make sure this is working. And it has to be in this emulator somewhere, right? Well, let's go to our main method. And I don't know, we say starting emulation, we input the shortcuts list, and we feed multiple. Let's just do a print line right here. Right? Is feed multiple all of a sudden much slower? Because this used to run like almost instantly. Or is it stalling? Like, did we break the recursion there? It's possible that we broke the recursion and ended up in an infinite loop. So let's jump to the definition of feed multiple. Oof, even jump to definition is slow. Okay, it's partially my computer's fault. Your old solver didn't used to work in aneurysm 9's binary. So you went through recently made generic. Oh, cool. Yeah, I'll be curious what about it wasn't generic in the first place. If you can say that spoiler free, I'd be. You probably can tell me spoiler free, but if not, then that can wait. No, I don't imagine you do it spoiler free. If you had to do it specific to your binary, then it was probably specific to certain addresses in your binary. So I don't imagine that's actually spoiler free. But that information in itself is a spoiler. Um, we can at least infer that knowing particular addresses is important. Fair enough, fair enough. Oh, my computer. Ah, and now we're not compiling. Okay, I'm gonna do this at least. I'm gonna turn off my camera for a second. Maybe that will save some processing power. I don't know. What else can I turn off? I don't have any ridiculous background apps. Yeah, compilation shouldn't take that long. We can at least still edit text here. Okay. So we should at least get to that line quickly. I don't have any reason to believe that this is going to be slow. This does follow with a progress until blocked. Right, this does a feed, a progress until blocked followed by a feed. So we should make sure that this is also performant. And this is fine. This is not doing anything fancy at all. This is a tail recursive function um, that just loops here. Oh, wait, I collapsed two cases. Do you remember when I collapsed continue and output? Well, continue and output aren't actually the same. Let's undo this diff. Can I do it from... Yeah, let's revert this. Yeah, they are not actually the same. I was hiding my output. That's what was going on. Um, okay, but we can still do like if stuff based on... Well, whatever. Just for the sake of it getting at work, we can always refactor this later. Okay, we're gonna do this. We're just gonna copy and paste all this code everywhere. Okay. It's not that it's hanging. Right, the AOU shows here. It's not that it's hanging, it's literally just waiting for input. Oh, I see. Aneurysms was from OSCON, and then Xenos was from the website a few years later, so it's a little bit updated. Makes sense. Hmm. I wonder if the specs are different. The specs are completely the same, right? Oh yeah, let's go. We need to reintroduce the opq that we removed here. So it's tick and then string and then a queue of string for all the ops that were being run. And there's an opq param here. So ops is a queue of string that defaults to queue.empty. Okay. Next stream, I might actually end up delaying the bytecode for a bit. The bytecode exploration, because there is some cleanup I want to do in here. Okay, and what's going on here? We need to return all the things. So we need to return the tick, the char string, and then the ops. Okay, that should compile now. Ignoring Noam Chomsky's contribution, Anna has hundreds of free Scala books. Um, I failed to see why Noam Chomsky would have contributions. You're making a joke that's gone over my head. But I did hear about Chomsky being somewhere in the Epstein files, which is a huge surprise. Okay, we are in Synacor. We're in the ruins. Right now, we have the teleporter. I'm going to use the teleporter. Okay, so that gets us here to the headquarters. And now, like, every time we use a teleporter, it should be the same, right? So if we turn to logging on, um, so toggle op log, and then use teleporter. Nothing like we start at one place at a place, we're ending at the same place. So the state before and after I'd expect to be identical, right? Unless it's like secretly tracking some other state. Interestingly, it is hanging here because I turned the op log on. So do things happen differently when I turn the op log on in a way that's important? Let's see. Um, progress until if op log enabled, we're still ticking along in the right way. Okay. And over here, yeah, we're still doing that. Shouldn't be expecting input. Why would it be hanging? Is it waiting for input right now? Look. Let's see if my custom commands work. So let's say toggle op log. Toggle op log. Okay, so it's not just hanging. It's not hanging. It's that when we have op log enabled, well, let's see. We don't end up printing. Oh, when we have oplog enabled, we don't end up printing output. So we're gonna toggle oplog again, make it false, and run the teleporter. Okay, so use teleporter. Anna's archive. Ooh, good to know. Okay, right. So the game still works. So use teleporter. We can do that as many times as we want to. Okay. Um, well, before we do anything else, let's clear my record. So clear oplog, and then let's look. Okay, we're still at the Synacor headquarters. Um, I want to figure out why we're not printing when oplog is enabled. So if oplog enabled, like we should still be adding, in either case, we're adding characters to the history queue, right? So here at the end, we have our next, we have our output. Um, we still progress our state, and we still add our output to the output queue. And we are still looping with our characters. Oh, yep, there it is, right here. We forgot to enqueue in this case. Right, there it is. Okay, so let's reload that. $61 million books. I appreciate knowing about Anna's archive. It's been a while since I've been able to find free books handily. Okay, so let's use a teleporter. And now teleporting from Synacor headquarters back to Synacor headquarters. Let's log that. So toggle the, what do we call it? The op log. Okay, now let's use the teleporter. Okay, cool. And then let's show the op log. What? That was tiny. Look at that. No way. That's way too small. That makes me feel like we are missing ops. Because there are no way there were that few ticks. Which reminds me, you know what? I might like to count the number of ticks. Let's add that to our, before I forget, let's add it to the wish list. Let's see, count ticks between commands. Yes, that was a vanilla teleport. But see, what gets me about that being that short is that I would have thought that the ops that I logged would also include writing all of this again, right? So I used the teleporter, right? I was waiting for input, then it consumes the input, and that's all logged, and then it should print all this output. And while it's generating all that output, it should be logging that. So this in itself is many commands, right? Because this is output one character at a time. So it should be at least this character many commands. So I'm not sure what actually got saved. So when I progress until blocked, if it's continue or if it's output, we save um, the state.show. State.show is a misnomer. It's like show. It's actually show instruction. So we could leave a note there, but to do rename show instruction. I'm not gonna do big renames right now. And oh, sparkly dark matter. Have a good night. Um, whatever the conclusion is tonight, you'll be able to see it at the start of tomorrow night. So, by the way, I had said I would take weekends off. I might very well stream tomorrow. So we'll see. I'm giving myself an opportunity not to stream tomorrow if I choose not to, but I might just do it through the weekend because I want to get this done before the 25th. Old AOC style. Um, What is going on here? In fact, you can probably turn my camera back on. What am I missing here? Is this a game binary input file? Oh yes, thank you for explaining that. Oh, when you run the binary, it just loops and prints a message? Well, I think you need to implement more opcodes in your VM. So let's look here. What ticks are we missing? We enqueue the show in either case here, right? Either continue or output. We shouldn't have an in or halt. We're not worried about handling that. And the same thing when we're doing input, we enqueue that. Oh, am I not adding to log input history.enqueue input? No, oplog.enqueue all. Yeah, that's what I'm missing. So that means that this code was I typed look, and that must be what's going on here, is that we were taking all the input. This is the stuff that happened in between that, I guess. Okay. And for the out, we actually need to enqueue the ops that we collected. When I reverted the code, yeah, here we go. Oplog dot enqueue all ops. Man, my IDE is not at all snappy. Okay. So, that's the last thing it prints without knowing more. Oh, thank you for handling that. So, we try this one more time. I think this is a time when we will finally see the binary that runs in between each of these. Okay, we use a teleporter. And then we toggle our oplog, use teleporter, and then we show oplog. What? Wait, we didn't queue that, right? Enqueue all ops. Did this actually compile? Did we actually save the file? What are our parameters? Progress until blocked. And when we copy, oh, this is input history. We're queuing into the input history. So oplog equals oplog.enqueue all. I need to have combinators on the state. So I'm not just using the copy constructor everywhere, because that starts to get confusing with this many parameters. I think between this stream and next, I'm going to go around and I'm going to spruce things up a little bit. Just all the little cleanups that aren't all that interesting, and we'll leave the interesting rewrites and refactors for the stream. Okay. So there's a output queue. Yeah, let's give those parameter names. History. We'll stay onto history. Okay, make that a little bit more explicit. Okay, this time, I think this time we get to see it. Use order. Okay, and then now we toggle uplog, and then we use teleorder. Okay, great. Now we show uplog. Hold on, I want to see the settings, like my shell history size. I want to make sure that's big enough I can get everything. So like under rendering, well, I mean, if it turns out, you can always fix that later. That can be an in-between streams thing. So let's show the oplog. It didn't seem like it was that big. Or like it printed pretty fast. Does it fill my history though? We got it. We got it. This is an important milestone because now this in here somewhere has the code that we need to analyze. And in fact, you can kind of see some of the structure. So there's a lot of like return happening here. It looks like this is a function that's being called over and over again, right? So there's some sort of a loop or recursive function. So we keep seeing the same pattern. In fact, just this in and of itself might be worth saving. Yeah, I'm gonna save all of this. That function might be worth decompiling. So it's already helpful. Okay. Add just an add greater than jump if true. Yeah, not sure what it's doing, but it is running that computation over and over again. I think I want to know how many lines are in the opcode oplog. That would let me diff things pretty quickly. So between two different jumps, if I change the register value and just ask how many, the size of the oplog, because we can't diff them right away, but we can at least know if it's worth diffing. Yeah, maybe like the size and the hash of the oplog would be nice to have. So let's do that. Let's go to the main. This isn't something that we need to make a method for. So case size oplog. And we can do type line. How many instructions run? So we can do emu.add oplog dot size instructions ran. Okay. And then maybe the hash of the oplog. And then we can just do emu.oplog.hash hash code. There we go. You oak larch olive. You have so many references I'm not familiar with. It's a red Sinclair calculator LED. Over my head. Um, so once again, we use a teleporter. At this point, I should just save that into my save state. And now we're going to turn on the oplog. So enable, or no, toggle oplog. And then we're going to use the teleporter. And then you want the size of the oplog. And we want the hash of the oplog. Okay. And then now let's clear the oplog. And just to check, we'll check the size of the oplog. Okay. And now let's get R8. That should be 0, right? Let's set R8 to 42. Get R8. Okay, so we've changed the register value. Oh, Brave, thank you for the follow. It looks like I've hit 400 followers, a nice square number. Thank you, I appreciate that. Brave Traveler, you are my 400th follow. Okay, so here, moment of truth. What we're about to do is run, I guess it's not the moment of truth. Let's just lower the stakes a little bit. We've cleared the oplog. We've reset the value of 8. So we're going to use the teleporter and see if the instructions that ran are different. Like see how many instructions ran, see if it's worth diffing basically, and check the oplog. And I think next stream we'll focus on maybe diffing between those and maybe decompiling the bit that we saved. Or, maybe decompiling the diffs. Maybe it's the diffs that matter, right? So let's use the teleporter. Or wait, I think we need to make sure the oplog is enabled. I think it is already enabled. Let's do a couple toggles. Toggle oplog. Okay, toggle oplog. So oplog is on. We can use the teleporter. Okay, and now let's look at the size of the oplog. 11633 instructions ran. Okay. And hash of the oplog. Okay, cool. It's exactly the same no matter what the value of the oplog is. What the value of the R8 is. Cool. That is good to know. I would like to diff memory. Probably diffing memory doesn't matter so much. But I don't know. I still don't know exactly where I want to diff memory. But yeah, we know what it is that we want to decompile. It is whatever is in that thing. Or at least we can look for, next time we get on, we can look for points of interest within those addresses. We can look at this code that's running over and over again in a loop and try to make some sense of that. Yeah. So let's summarize what we did, and then I'll find a stream to raid. So if anyone has suggestions, know anyone else that's on, maybe doing something to do with assembly or emulators, please drop that here. Okay, our README. What did we do today? I think we actually did quite a bit. We haven't done interdimensional physics yet, so this is not our episode title. But we added ability to print a VM states currently running instruction. Added an op log to our emulator. Recorded instructions that run when using the teleporter. Okay. That's basically what we did at a high level. I feel like there were so many littler things you're doing within that. But our oplog did take multiple instructions. And the printing took some time. And it unlocked potential bonus goals. One is having ASM, like no ASM DSL, an AST for our VM transitions, or for like the construction of basically it's the interpretation of machine code forms an AST, because interpretation of machine code could mean a few things. It could mean this is how you could have an interpreter all over that AST that gives you the machine code decompiled to assembly, or you'd have something that gives you your state machine transition. So yeah, it's not exactly a VM state transition AST. It could also be machine code AST. Yeah, something like that. Machine code interpreter. I much prefer writing interpreters than writing, all this code. We've written way too much code. And I'd love to delete some code. Great. And our goal at the start of the next stream. Oh, count ticks between commands. That's still a worthy goal. But our main goal is to start disassembling that bytecode. And for that, we might want to write to a file, which I know. We'll get there. We'll get there. You'll need a lot more to get the necessary features. Fair, fair. I appreciate your help there, Zuno. Okay, let's go find someone to raid. Oh, bad cop's on. Postfix incrementing my C. Godot dungeon crawler. Day of grinding boot.dev. Sergeant Pepper is on again, doing more of their refactoring in Rust. Yeah, no, thanks for being here. Thanks for all the help with the debugging and the questions. That really helps keep me on track. Let's trade bad cop. Wait, invariant of disruptive systems enter. I'm not sure what that is, but bad cop is familiar and probably knows a little bit of what we're doing here. There'll be an emulator, then now I become destroy rules guy. Fair enough. Okay, so raid bad cop underscore. All right. Thanks, everyone. Have a good night. I'll click it. And I should be watching the actual stream. You don't know. She might be about to end. Oh, Flappy Bird in the terminal. All right. Let's make sure I end this stream. Good night on YouTube if you're still hanging around. I appreciate y'all coming in from that side.